This is the first video in the module on oscillations, which is a very important topic in physics for at least a couple of reasons. First of all, harmonic oscillators in particular, which we are going to study extensively here, is one of very few problems that we know how to solve under almost any circumstances. Second, oscillators are extremely important in all areas of physics, not just mechanics, where you of course can have mechanical systems oscillating, as you are well aware, but they matter far beyond that. For instance, in quantum field theory, fundamental particles, elementary particles, can be seen as excitations on harmonic oscillators. Light is a wave, which is a form of oscillations, etc. We have already studied the case of the harmonic oscillator, even though we didn't call it that, when we had a potential which took the form 1/2 kx squared plus a constant, which is unimportant. When it comes to potentials, you can always just add a constant to them, and that doesn't change any of the physics. So we know that in this case, if the potential as a function of x, and we're restricting ourselves to one dimension here, if the potential is 1/2 kx squared, that gives us that x as a function of time has this form. As we showed earlier, we also know, of course, that since the force in the x direction is going to be minus the derivative of the potential with respect to x, that means that if the potential looks like this, then we get that the force is minus kx. Graphically, we can look at the slope here, like the force is the negative slope. That means that we have forces on the left here that are pointing towards the equilibrium, and also on the right, so that any particle that is deviating from the equilibrium point here at the bottom feels a restoring force, and that's what gives rise to the oscillation. And this is what the force looks like if you plot it. For a harmonic oscillator, it's just a straight line with slope minus k. And this is an example of Hooke's law. Hooke's law says that, for instance, if you have a spring, then the force on that spring is proportional to the negative displacement from equilibrium. However, this type of force, this type of potential, has importance far beyond just perfect harmonic oscillators or perfect parabolic potentials. It turns out that Hooke's law describes oscillations for small oscillations, small displacement from a stable equilibrium in almost every case. To see how, let's take a potential that is not perfectly parabolic. It's this potential here, and I'm going to actually say that x equals 0 here, right at the equilibrium point, just to make the math more simple, but that's not necessary in general. We just do it here for simplicity. So what we can do is we can expand this potential around the equilibrium point. So this is the equilibrium point, x naught. And so I'm going to say that we have a stable equilibrium at point x equals x naught equals 0 for simplicity. I can then do a Maclaurin expansion, or Taylor expansion. It says the potential near this point here, 0, equals the potential at 0 plus the first derivative of the potential at 0 times x plus 1/2 u double prime of 0 and x squared, etc. This is known as the Maclaurin series. So first of all, what we have here is this first term, u of 0. Now that's just a constant, so that's unimportant. Remember, you can take a constant and add it to any potential. It doesn't change any of the physics. That's because the force is the spatial derivative of the potential. So if you take the spatial derivative of a constant, obviously you get nothing. We'll look at the second term here. Now, the first derivative of u at 0, which is where we have our equilibrium, that's going to be 0. Because we are at the equilibrium, you can see that the slope here is 0. And then finally, if we look at the second derivative here, we know that's going to be greater than 0 if we have a stable equilibrium. So, and then we have higher terms, but they can be ignored. They are on the order of x cubed. So for small motions, this can be ignored. So what we end up with then is that we have that the potential of x near the equilibrium is approximately equal to some constant, which we don't care about, plus 1/2 kx squared, where k is just u double prime at the equilibrium point. So this is equivalent to saying that the force x and the force of x, the force of the function x, is approximately equal to minus kx, which is Hooke's law. Once again, and that again is valid because we're making the approximation that x is small. So we have that x is small. That means that x cubed terms can be, and higher order can be neglected. In the Taylor expansion of u. And that gives us Hooke's law, which, as we know, gives us harmonic oscillation. We can see this graphically as well. If we just plot the force, which we find by taking the derivative of the potential with respect to position. So here's f of x, which is minus u prime of x. And we can see here that if we're close to the equilibrium point, then what we have is a straight line with a negative slope, just like what we had in the case of the perfect harmonic oscillator. So for small enough displacements around the equilibrium, what we have is something that behaves exactly like a harmonic oscillator, or it behaves like a harmonic oscillator, at least with a very good approximation. So that should motivate why we are interested in harmonic oscillators. Now let's just solve the harmonic oscillator problem one more time. We did it earlier when we worked with potential energies. We're going to do it again now from a force perspective. So if we have that Hooke's law is valid, let's say just to be concrete that we're dealing now with the case of a mass on a spring. And we have forces on this mass that come from the spring. So those forces are going to be minus kx. Right? If the mass moves to the right, then there's a started force towards negative x. If it moves to the left, there's a force that pushes it back towards positive x. So that's described by this formula. We have Newton's second law, which has, of course, that mx double dot equals this force, which is then minus kx. So x double dot is minus k over m times x. And I'm going to rewrite this suggestively as minus omega squared x, where we just have taken to define omega as the square root of k over m. And then we can see that this has the solutions of x of t equals e to the I omega t. That's the first solution. And x2 of t equals x e to the minus I omega t. So those are the two linear independent solutions to this linear differential equation, something you should already be aware of. It's quite easy to see. We can show it here just by simply taking the derivative of this twice. So first we look at x1 dot. It's going to be I omega times e to the I omega t. X double dot of 1 is therefore I omega squared times e to the I omega t. I omega squared is minus omega squared, and then e to the I omega t, then well, that was x1. So that's x1. And we can do the same thing for x2. So this is these are the solutions here to this differential equation. All right. This means then that the more general solution, and I'm going to rewrite the equation of motion here. If we have that x double dot equals minus omega squared times x, that gives us in general that the full solution is a linear combination of these two possible solutions. So that will be c1 times e to the I omega t plus c2 times e to the minus I omega t. And that's a perfectly fine solution to the differential equation. Now we can solve this, we can write the solution in a different form if we like. We note that plus minus I omega t, that's going to equal to cosine of omega t plus minus I times sine of omega t. It's a basic result that you can find in the complex numbers video if you're interested. So because of that, we can, if you like, rewrite x of t as c1 times plus c2 times cosine of omega t plus I times c1 minus c2 times sine omega t. And if we take if we choose the constant c1 and c2 properly, then both this and that becomes real, and that makes sense because position is a real number. And then we end up with a solution that x of t equals b1 cosine of omega t plus b2 sine of omega t. So that's yet another way to write the solution to this differential equation. Which one you choose, whether you work with this solution or that solution, depends on what is convenient at the time. This one, however, describes the physical situation because we can choose b1 and b2 to be real, and then we get a real number. Here we have to work a little harder to make x real. So in the next video, we're going to study these solutions in some more detail. But you need to be very familiar with all the forms, this one and that one, and a couple of others that we're going to introduce shortly, because you will see this equation many, many times in this course. And you should basically learn this by heart.